Fine. So yesterday we discussed about power distribution, power optimization, and signal integrity issues. So we ended our session with defining two aspects of signal integrity, where we defined integrity as purity of a signal. So this is one aspect of signal integrity where we define two terms, that is controllability and observability. So these two terms were defined in relationship to the ability of pins on an IC. So we have defined controllability as the ability of an input pin of an IC to assign logic 1 or logic 0 value to a particular node of the chip, that is inside the chip or inside the IC. While we define observability as the ability of an output pin of an IC to deliver logic 1 or logic 0 value at the output node on the chip to the real world. Okay, so we can basically say that controllability speaks about writing operation. Okay, so we can say this is speaking about ability to write data, and we can say observability refers to ability to read data. Okay, so okay, so today we touch upon some other signal integrity issues, um, which I could not cover because already the lecture had extended 15 minutes. So we'll cover them today. Okay, and once we discuss about the pending topics under signal integrity, we will discuss a very interesting topic called as hazards. So we will be defining hazards, we will be enlisting the different types of hazards. We will take one circuit example which is suffering from this problem of hazard, and then ultimately the solution or elimination of hazards in a circuit. Okay, so So we define signal integrity as the purity of a signal. So we can say that a signal inside a chip can get contaminated because of many sources. Okay, so we can say signal integrity or purity is disturbed mainly due to different noise sources. The first source is reflection noise. So it occurs due to impedance mismatch, stubs, vias, and interconnect discontinuities. Okay. Second is called as crosstalk noise. It's not traces, it's tracks, signal tracks. So we had defined vias as vertical interconnect architecture. So interconnects usually connect components which are existing on the same layer, and VI is used for connecting two components which are existing on two different layers. Okay, so it's VIA. Okay. Third is power or ground noise. Parasitics. Already we have discussed this. This is called as in addition to the above three noises, that is reflection noise, crosstalk noise, and power ground noise, we have EMI, EMC also responsible for signal impurity issues. Okay. Also, the electronic packaging used in modern day microprocessors or microcontrollers or FPGAs having more than 2000 pins finding applications in gigabit networks and say 5G and okay. So these were some additions for signal integrity. We can add it in yesterday's definitions of controllability and observability. Okay. Now you go to today's topic, that is hazards. Okay. Basically, hazard in English means danger. So that is why when we say that this particular system or this particular circuit is suffering from an hazard, that means it has a certain kind of a danger. So we will see that this particular word hazard, why it is said that why this word basically used for circuits. Okay, so we say that this is a hazard affected circuit or this is a hazard free circuit. So we will come to know what is the meaning once we discuss what are they. Okay, so usually hazards is a problem. So let us put it down like this. Hazard in English actually means danger. So it is an unwanted effect in a digital circuit. Okay, so hazard basically it is an unwanted effect in a digital circuit, usually affects, usually found, not affects, usually found in combinational circuits in combinational digital circuits and asynchronous sequential circuits. Okay, So it's an unwanted effect. It is found either in combinational circuits or asynchronous sequential circuits. Basically appears in the form of unwanted switching in the output signal. Okay, please note this, that basically this hazard effect appears in the form of unwanted switching in output signal. So you will, although we see that there are different types, still we'll come to know that basically you will see unwanted switching here. So there are basically two types of hazard. So basically hazard effect appears in the form of unwanted switching in an output signal. So when this output switching is only once, then it is called as a static hazard, and when it happens multiple times, it is called as a dynamic hazard. So we will give examples now. Okay, so basically hazard is also known as danger. It is an unwanted effect in a digital circuit, usually found in combinational digital circuits and asynchronous sequential circuits. Basically appears in the form of unwanted switching in the output signals. Okay, and another thing is that this switching is actually temporary. Okay, it is temporary and short-lived switching. Okay, so it is a temporary and short-lived switching, something like in power electronics or in the mains we have transients coming. So it's suddenly high voltage will come, but it does not exist forever. It occurs for a few milliseconds only, not milliseconds, few microseconds. Similarly, when the digital circuit is supposed to have an output equal to 1, it goes to 0 for some time. That is one example of a hazard. Similarly, if the output is supposed to be 0 but it becomes 1 for a short period of time, that is also again called as an hazard. Okay, and what is the ultimate consequence of hazard? It leads to malfunction of the circuit. Okay, presence of hazards leads to circuit malfunction. Okay, yes. So now we go to the second this thing, that is types of hazards. Static hazard and dynamic hazard. Okay, static hazard in turn is of two types. static 1 hazard. Similarly, we have a static 0 hazard. Okay, so first we'll define static 0 and static 1 in a very simple way, and then we will draw the waveform so it will become very clear. Okay, so static 1 hazard means stable value is equal to 1 becomes unstable, that is 0, and returns back to 1. Okay, I repeat. The static 1 means what? What is the behavior? The output stable value is 1, it becomes unstable, that is 0, and then returns back to 1. Okay, similarly, we can define static 0 as output stable value is 0 becomes unstable, that is 1, returns back to 0, returns back to 0. Okay, the static 1 means the output's stable value is 1, it becomes 0, that is unstable for a very short time and returns back to 1. Static 0 hazard means the output's stable value is logic 0, it becomes 1, that is unstable for some time and returns back to 0. So if you want to make waveforms for this, then we can make it like this. Okay, so we can say output is stable at 1, it becomes 0 for some time and then becomes 1 again. Similarly, here the stable value is 0, it becomes 1 for some time and returns back to stable value. Okay, so we can say 1 0 1, 0 1 0. Okay, and we can say this is stable state, unstable state, stable state, stable, unstable, stable. So we'll say S means stable, US means unstable. Okay, fine. And here in case of dynamic, so we can basically say that 1 and 0 are the expected outputs. Similarly, in case of dynamic hazard, the output is supposed to change from 1 to 0, only one transition. But instead what happens is it goes like this, it goes 1, okay, it goes it goes 1 to 0, 0 to 1, and then it comes to 0. Okay, so here there is only one transition. Okay, there is only one transition. Here there are 1, 2, and there are 3 transitions. Okay, so in dynamic hazard the output is supposed to only make single transition from 1 to 0, but instead it makes 3 transitions and then comes to 0. Another more severe example would be having 5 transitions. So 1 to 0 to 1 to 0 . So 1 to 0, 0 to 1, 1 to 0, again 0 to 1 and 1 to 0. Okay, so here we have 5 transitions: 1, 2, 3, 4 and 5. Another example of a more severe dynamic hazard. Okay, now it's clear that there are two kinds of hazards: static and dynamic. Static is again classified as static 1 hazard and static 0 hazard, wherein in static 1 hazard the output is stable at 1, static 0 hazard output is stable at 0. But in case of static 1 hazard, the output momentarily becomes unstable, that is goes to 0 and returns back to 1. Similarly in static hazard, it momentarily becomes unstable, that is logic 1 and returns back to 0. Dynamic hazard, the output is supposed to make a single transition to go from 1 to 0. Instead of that, if it makes 3, 5 or more transitions, it is known as a dynamic hazard. Okay, now we are going to discuss a circuit which suffers from a hazard and then how to eliminate the hazards. Okay, fine. Okay, so consider the following and find if it suffers from hazard. Okay, consider the following combinational circuit and find if it suffers from hazard. Okay, fine. Very simple circuit. The first input x1, second input x2, third input x3. Okay, so we will say let this gate be G1, the second AND gate G2 and the OR gate be G3. Okay, so let us also define outputs now. So x1 and x2 are the inputs to the gate G1, x2 bar and x3 are the inputs to the gate G2, and the outputs of the AND gates are acting as inputs to the OR gate G3. So we will define this output as y1, this output y2, and let us say the final circuit's output, the final output is y. Okay, so now we can also put down equations here. So we say that y1 is x1 ANDed with x2, y2 is x2 bar ANDed with x3, and the final output y is the ORing between y1 and y2. Okay, keep these equations in mind now. Y1 is x1 and x2, y2 is x2 bar and x3, and y is y1 or y2. Okay, now we make certain assumptions. Okay, case 1, x1 equal to x2 equal to x3 equal to 1. Okay, so we want to find out that what is the value of y. So if x1 equal to x2 equal to x3 equal to 1, then we want to find out what is the value of y. It's very natural. We can either put the values here, or we can also compute equations number 1, 2 and 3. Okay. So equation 1, equation 2 and equation 3. Okay. So from equations 1, 2 and 3, we can say that y1 is 1 ANDed with 1 equal to 1. y2 is x2 bar, so it is 1 bar ANDed with 1 equal to 0, and we can say y is 1 odd with 0 equal to 1. Okay. So 1, 1, 1. Okay, so we get 1 here, we get 1 here, we get 0 here, and we get 1 here, we get 0 here, and we get 1 here. Okay, so for x1 equal to x2 equal to x3 equal to 1, the output of the circuit y is equal to 1 as per equations 1, 2 and 3, and even from the schematic diagram. Now we take case number 2. Case number 2 is that the input x2, this particular input x2, it changes from 1 to 0. So I'll write it here. We have x1 equal to x3 equal to 1, and x2, it changes from 1 to 0. Okay. Second case, x1 and x3 remain unchanged, but x2 actually changes from 1 to 0. Okay, again according to equations 1, 2 and 3. Okay, y1 is x1 ANDed with x2. So now the new value of x2 is this. Okay, so now x2 is 0 now. So y1 is equal to x1 ANDed with x2 equal to 0. y2 is x2 bar, so it is 0 bar ANDed with x3. Okay, that is equal to 1, and my y is now equal to 0 odd with 1 equal to 1. Okay, so now in both case 1 and case 2, the output of the circuit has come out to be 1. Okay, so here again I get output equal to 1. Okay, but here we have made an assumption. What is the assumption we have made? The assumption which we have made here is that when x2 changes from 1 to 0, the NOT gate instantaneously complements it. Okay, so here I will write that here in case 2, it is assumed that the NOT gate complements x2 without any propagation delay. But you read the datasheet of any logic family, that datasheet clearly mentions that the logic gate always has a non-zero propagation delay. If you take TTL logic family of 20-25 years ago, the standard propagation delay of TTL logic family is 10 nanoseconds. Now naturally, because the systems have advanced, transistors have become more efficient, more fast. That is why propagation delay has reduced, but still it is not zero. Okay, so we should understand that logic gate always offers a non-zero propagation delay. It is where TD is not equal to 0. Okay, so now what we will do is that we will analyze case number 2 again, by now assuming that there is a finite time taken by this NOT gate to convert, 0 to 1. Okay, so now what we will do, we will say now x2 has changed from 1 to 0, so naturally 0 to 1. Okay. Not what we will do is that we will draw the waveforms. We will draw the waveforms directly. X1, X2, X2 bar, X3, Y1, Y2. Okay. Okay. Fine. Okay. Directly we will analyze case 2. Okay. Case 2. So we have x1 equal to x3 equal to 1 and x2 was 1 and it changed to 0 at some instant. Okay, fine. So now x1 equal to 1. Okay, fine. Let us write the signal names first. X1, X2, X2 bar, X3, Y1, Y2 and Y. So x1 and x3 are 1. Okay. x2 is also 1 for some time. x2 is 1 for some time, and then it goes to 0. Okay, fine. So x2 bar will be opposite now. Okay. But here what I'm doing is that I'm assuming that the inverter is actually offering some non-zero propagation delay. You see here. So actually I was supposed to change x2 bar from 0 to 1 at this instant. But what I'm doing is that I'm extending it little bit here. Okay. Here. And now from here it is complementing. Okay. So I will denote that this is the propagation delay of the NOT gate. Okay, now it's very simple. Now we'll start doing y1 and y2. So y1 is ANDing between x1 and x3. So it is x1 dot x3, y2 is x2 bar ANDed with x3, right? Yes. So it's very simple. The waveforms are very simple now. So y1 is x1 x3. So x1 x3 are constant. So throughout it will be like this. Okay. So because x1 and x3 are always 1, so y1 will always remain 1. Now y2 is x2 bar and x3. So basically it's ANDing between this and this waveform. Okay. So it's very simple again. So x2 bar and x3. So till this point it will be 0 and then it will become 1. Okay. So sorry. X2 bar and x3. Sorry. Okay. So now the output y, it is ORing between y1 and y2. It is y1 ORed with y2. We can clearly see that when y do ORing between these two, then yeah. So 1, 1, 1, 0, 0 and 1. Actually, you never pointed out. I made a mistake here. Okay. I think so. People are not just attending the class. Y1 is x1 and it is x2. X2. So x1 and x2 is there. So we have to do the ANDing between these two signals. Okay. These two signals and then these two signals. So those two signals are y1. This is actually y2. Okay. Okay. So now it's clear. 1, 0, 0, and this is 1, 0. Okay. So 1 odd with 0 is 1, 0 odd with 0 is 0, and 0 odd with 1 is 1. So now we see here 1, again 1, and here we have, here there's a hazard now, 1, 0, 1. Okay, so it's 1, 0, 1 represents static 1 hazard in this circuit. Okay, so we are told that if the output is supposed to remain 1 and goes to 0 and returns back to 1, it is called as a static 1 hazard. Okay, yes. So we conclude that since output y goes to 0 for t equal to propagation delay of NOT gate and returns to 1 again, the above circuit suffers from static 1 hazard. Okay, now I can convert this circuit. If you know from second year, we also know from second year that this is same as not okay, and we also know that is same as a NAND gate. If I put two NOT gates on this path and two NOT gates on this path, then the first inverter and this AND gate will form NAND. Similarly, the second inverter and the OR gate will form a NAND. Okay, fine. So we also know that this particular structure is actually equal to a NAND gate. Okay, why? because we say that bubbled OR is NAND. Okay, so redrawing circuit using NAND gates only. So because we have replaced AND with NAND and also the OR with NAND, this circuit will functionally remain the same as above, but it will start suffering from static zero hazard. Okay, so okay, fine. So about elimination, we'll discuss in the next lecture.